new Lambert's law. This is the second topic in the first unit of analytical instruments. So here we are going to discuss about derivation, that is will be deriving. It's a very simple law only, Bayer-Lambert's law, and explanation for the Bayer-Lambert's law and limitations is going to be discussed here. The experimental measurements were usually made in terms of transmittance T, which is defined as T equal to I by I naught, where I is the light intensity after it passes through the sample and I naught is the initial light intensity. You can able to understand what is I and I naught from the given picture, and the relation between A and T is, that is A is nothing but absorption of light by a sample, A equal to minus log T, and which is equal to minus log T can be replaced by this equation I by I naught. Modern absorption instruments can usually display the data as either transmittance or percentage transmittance or absorbance. An unknown concentration of an analyte can be determined by measuring the amount of light that a sample absorbs and applying Bayes-Lambert law. If the absorptivity coefficient is not known, the unknown concentration can be determined using a working curve of absorbance versus concentration, which is derived from the standards. And other form of Bayer-Lambert's law, A equal to ECB, where A is absorbance, no unit, since A equal to log 10 P naught by P is either P naught by P is the another form of absorbance. We can use the previous one also, I naught by I. And E is the molar absorptivity with units of L, mole to the power minus 1, centimeter to the power minus 1. And B is the path length of the sample, that is the path length of the cupboard in which the sample is going to be contained. And we are going to express this measurement in centimeters. C is the concentration of the compound in solution and expressed in mole per liter. Mole per liter. Liter to the power minus 1 and this is nothing but mole per liter. The reason to express the law with this equation is because absorbance is directly proportional to the other parameters as long as the Bayer-Lambert's law is obeyed. Okay. Derivation of the law. I naught is the, actually this is also the another form, already we have discussed this one. I naught is the intensity entering the sample at Z equal to 0. Iz is the intensity entering the infinitesimal slab, this one, infinitesimal slab at Z, and L is the intensity absorbed in the slab, and I is the intensity of the light leaving the sample. Then the total effect area on the slab due to the absorbers is sigma into N into A into Dz. Then the fraction of the photons absorbed will be sigma into N into A into Dz divided by A. So di by Iz equal to minus sigma N dz. Integrating this equation from z equal to 0 to z equal to d gives natural log of I minus natural log of I naught, which is equal to minus sigma N d, which can be written as minus natural log of I by I naught, which is equal to minus sigma N d. Since N molecules which is multiplied by 1 mole, which is multiplied by 1000 centimeter square liter per centimeter square per liter, which is equal to, will be getting, that is, the N is going to be replaced by this equation, 6.023 into 10 power 20 divided by 2.303, okay, into Cv. It can be given as minus log I by I naught in left hand side, which is equal to A, which is equal to epsilon Cv, where epsilon is sigma into 6.023 into 10 power 20 divided by 2.303. Limitations. What are the limitations of the Bayer-Lambert's law? This is an important question, maybe a 4-mark question. The linearity of the Bayer-Lambert law is limited by chemical and instrumental factors. The causes of nonlinearity. Why the nonlinearity is going to occur? That is including the following points. The first point is going to be deviation in absorptivity coefficients at high concentrations, that is, which is greater than 0.01 mole due to electrostatic interactions between molecules in close proximity. The second point is scattering of light due to particulates in the sample. Fluorescence or phosphorescence of the sample. That is also the reason. Then changes in refractive index at high analyte concentration. Next is shifts in chemical equilibria as a function of concentration. Then the next is non-monochromatic radiation. Deviations can be minimized by using a relatively flat part of the absorption spectrum, such as the maximum of an absorption pattern. And stray light, that is also a reason where your B lamberts or the thing become non-linearity, so that I could not able to use the Weir-Lambert law.